We talked about magnetic induction of current. So changing the magnetic flux within some area generates a current, but that's a very qualitative statement. How much of a current, how much of an EMF is generated through a changing magnetic flux. Well, Michael Faraday calculated what's called the law of induction. So it states that the EMF that's generated, remember the EMF is in volts, think of it as the potential across 2 points in a circuit, like a battery. The EMF that's generated by this magnetic induction of current is equal to the negative, and I'll explain why it's negative in a moment, the negative number of turns of wire, or number of loops of wire. So the previous video's demo at the end, I induced a current by moving a magnet through a loop of wire, but that set of loops of wire had 3,200 loops. The reason it had so many was so I could do a small change in magnetic flux, multiply it by the number of loops, which in that case was 3,200, to get a fairly substantial EMF out, to make the measurement easier to do. So every current is induced in every loop of wire, so if you have 10 loops of wire, you have 10 times the current, 10 times the EMF. So it's the number of loops of wire. It has to be at least one loop of wire to generate, an EMF. And then the changing magnetic flux with time, how quickly the magnetic flux changes with time. If the magnetic flux doesn't change, if the magnetic field stays the same with time, if the area stays the same with time, and the angle between the two stays the same with time, there's no EMF generated. It's only when the flux changes with time, by either changing the magnetic field strength, by changing the area, or by changing the angle between the two, that you get an EMF generated. Okay, so this tells us the magnitude of the EMF. What about the direction? For a loop of wire, what direction will the current want to go around in? Well, to do that, we introduce what's called Lenz's law. Lenz's law basically states that the induced EMF that's created by the changing magnetic flux induces a current and a magnetic field, because currents generate magnetic fields. So it generates a current and a magnetic field that opposes the change in magnetic flux. Think of it this way. A loop of wire likes to have the same amount of magnetic field going through it. So if you try to change that, if you try to reduce the amount of magnetic flux through a loop of wire, a current will appear to try to reinforce that magnetic flux, to keep it the same. It fails, but it tries. Or if you increase the magnetic flux through an area, the current will generate in the loop of wire to try to reduce that effect, to try to keep it the way it was. It fails, but it tries. So let's look at a simple example. We're going to have a magnetic field going into the board. So the red X's here represent a magnetic field going into the board. Imagine the magnetic field lines all pouring into the board. I have here a big U-shaped copper wire. It's not complete up here. There's nothing attached to those ends. It's just a big, measure like copper rails, like railroad tracks, connected together across using a simple wire. Now on these tracks, I have another conducting bar, but this bar I can slide back and forth. So the loop area A is the area inside these side walls and the bar. This creates a conductive loop, assuming all of these things are conductive. So I can change area A by sliding this bar back and forth, right? So if I slide to the right, I increase loop area A. If I slide to the left, I decrease loop area A. Magnetic field strength stays the same. I'm not changing those X's at all. The angle, I'm not spinning this in any way, so the angle doesn't change. So the only thing that's changing with time is the area. So what happens if I pull this to the right? If I were to grab this bar and pull it to the right, I'm increasing the area A, and I'm increasing the magnetic flux through area A, right? As I pull this to the right, I bring in more magnetic field lines. Magnetic flux is B times A times the cosine of the angle, right? I'm increasing A, which increases the magnetic flux, because more magnetic field lines go through the area. So a current will appear around this loop of wire to prevent that from happening, to try to stop the magnetic flux from increasing. So what way does that loop have to appear, the current have to appear in order to prevent the magnetic flux from increasing? Well, the answer is actually clockwise, and I'll explain why in a bit. So there's a current that will develop in a clockwise direction because, again, look at each of these wires, these four sides, as an individual wire. Use the right-hand rule for magnetic fields around a current of wire. Finger in the direction of the wire and grab. Oh, sorry, I did it backwards. Magnetic field is in the board. My mistake. It will be counterclockwise in this example. So as I pull this to the right, I get more magnetic field lines going into the board in that area. So a current must arise that gives me magnetic field lines that come out of the board inside that area. Using the right-hand rule, I didn't break the wire here, this is actually a complete wire. Fingers in the direction of the current, grab the wire. Around the wire, you can see my fingers come out on the bottom, out of the board. Here is the current I. Looks like an H on the side, these are all capital I's. I grab the wire, my fingers come on this side of the wire out of the board. Down here, fingers in the direction of the current, grab the wire around so this is the wire, I'm grabbing it, my fingers are coming out of the board. And again here, if this is the wire, I grab it, thumb in the direction of the current, my fingers come out of the board in area A. So a counterclockwise current will generate a magnetic field coming out of the board, which reduces the magnetic flux. Magnetic flux is the sum of the total magnetic field lines. If the same number of magnetic field lines are going into the board through area A and out of the board through area A, then the magnetic flux is zero. So current, Lenz's law states this current direction will oppose the changing magnetic flux. Now, that's if I push the bar to the right. If I push the bar to the left, if I pull it and close this area, I reduce the number of magnetic field lines in the area. I'm reducing the magnetic flux. And since I'm reducing the magnetic flux, a current will develop to try to reinforce the magnetic flux. So the current direction will flip. As I had it initially, it will go clockwise. And again, using the right-hand rule for currents, you can see that thumb in the direction of the current, grab the wire, my fingers go into the board in area A. Thumb in the direction of the current, grab the wire, my fingers go into the board, and that's true for all the sides. So a clockwise current puts more magnetic field lines into the board, reinforcing the magnetic flux as I pull this to the left. How much current? Well, it depends on the resistance in the wire and the EMF generated, right? It's Ohm's law. V equals IR, where V is the voltage across the EMF source. I is the current and R is the resistance in the wire. So the wire has some small, even conductors have some small value of resistance, unless it's a superconductor. It depends on the number of loops. Here it's just one loop, but imagine I had many, many, many loops of wire that I could pull aside. That would increase the EMF. And how quickly the magnetic flux changes with time. That's the important thing. It's not just the magnetic flux, it's how quickly it changes. So the faster I move this to the right or to the left, the faster the area A changes with time, the faster the magnetic flux changes with time, the bigger the EMF that's generated. And again, the example I did in the last video at the end showed that. The faster I move the magnet, in that case I was changing the magnetic field strength, not the area, but the faster I move that magnet, the bigger the needle jumped, the further the needle jumped, because it was a bigger EMF, therefore a bigger current was generated over a shorter period of time. And when I moved it slowly, you ended up with a smaller current over a longer period of time. But in order to induce a current, you have to change the magnetic flux. I want to get that across and drill that into your brain. It's not just that there's a magnetic field here. If I just left this alone and didn't change anything, no current would exist in this wire. But when if I change the magnetic field strength, or I change the area by moving this, or if I spun this, I would change the magnetic flux through area A and a current would generate. Your book talks about some applications for electromagnetic induction. Electromagnetic induction, remember, is a magnetic field changing in a loop of wire. So what you can do with this technology is generate an electrical signal in an object that's not physically attached to a power source. So for example, cochlear implants, your book uses that example. You actually have a surgical implant inside the person's skull, but the device on the outside of the skull records the sound in the area, encodes that as an electrical signal using Faraday's law of induction. A changing electric magnetic field in the outer portion communicates with the inner portion without physically having wires attached, because you don't want wires poking out of your skull, right? That's infection sites, that's where bacteria can get in. By isolating the inner sterile electrical equipment from the outer dirty electrical equipment, it's much safer. Pacemakers work in the same way. Pacemakers actually used to be able to, and this is sort of cool technology, if you had an embedded pacemaker, you could take your phone, put it up to your chest, and they would be able to actually check how the pacemaker is doing by using the microphone in the phone to actually communicate with the pacemaker, which is kind of an amazing technology. But again, a pacemaker, in that case, it does have a power source. A pacemaker has to have a power source to, of course, drive your heart, but it doesn't have to have a very powerful power source. Electromagnetic induction is also why people with pacemakers can't go around powerful microwave ovens. You'll often see warnings in like Quick Trip and things like that, or on the microwaves, where don't use if you have a pacemaker, because a very powerful microwave oven generates a very powerful induced changing magnetic field, which can induce a current in a pacemaker and cause your pacemaker to fail or to fire incorrectly. Inductive ranges. That's becoming more popular in modern kitchens. Rather than having gas, which is flammable, clearly, or having an electrical filament where sometimes it's hard to tell if it's on, you easily burn yourself, an induction range actually induces a magnetic field which can generate a current in a magnetic bottomed pot. That current, those were called eddy currents, we'll talk about those in a bit, will actually generate heat in that pot. So you can actually cook using an induced magnetic field. The advantage is if you turn the burner on and you have no metal on your hands, you can put your hands on an active induction range burner and it won't hurt at all, because your hand is not metal, it's not magnetic, therefore it won't generate any currents or heat in your hand. Copper bottom pots won't work, aluminum bottom pots won't work because they're not magnetic. You need a magnetic material to use on an induction range. And a quick way to check if you have a magnetic pot, stick a refrigerator magnet on the bottom of your pot. If it sticks, you can use it on an induction range. If it doesn't stick, you can't.